This video shows how to determine the voltage across a capacitor as we're charging the capacitor up. So here we have the original circuit, and there's a switch right here, and at time t equals 0 we're going to close that switch. And what's going to happen then is current is going to flow into this capacitor through the resistor and back into the source. So of course we will have some current flowing through the 24 kilo ohm resistor, but some of that current is also going to be flowing through this capacitor in the circuit. So the first thing that we need to do then is to create a Thevenin equivalent circuit. So if we break the circuit right here, and so we look at this point AB right here where we break the circuit, we need to find the Thevenin equivalent circuit. So we can find the Thevenin voltage by finding the voltage VAB when this section of the circuit is disconnected, as with the switch open as shown here. And so we can use the voltage divider rule to find V Thevenin, which is going to be the voltage across the 24 kilo ohm resistor there, which is our original E voltage of 20 volts times the 24 volt resistor divided by the total resistance of 32, I'm sorry, I said 24 volts, that was 24 kilo ohms, and divided by 32 kilo ohms, and that gives us 15 volts. Okay, so we have 15 volts is our E Thevenin. And then we can calculate R Thevenin. Remember, to determine R Thevenin, what you would do is short out the voltage source. So you would short out the voltage source, and you would calculate the resistance if you were to put an ohm meter and connect an ohm meter to points A and B here and measure the resistance. And in this case we would have R1 and R2 are in parallel. So R Thevenin is equal to R1 in parallel with R2, which is the 1 over 8K plus 1 over 24K, and that gives us 6 kilo ohms. So if we replace this section of the circuit here with the Thevenin equivalent, that gives us the E Thevenin voltage source of 15 volts with an R Thevenin resistance of 6 kilo ohms. So when you close the switch, so when the switch closes, then you're going to have basically a 15 volt source supplying 10 kilo ohm resistor in series with the capacitor of 15 microfarads. And so that is our RC charging circuit. So now once this switch closes here, we would be charging the capacitor. So we'll be charging. So we're going to charge this capacitor up. And so the time constant, tau, is the total resistance times the capacitance. Remember, for a charging time, the charging time constant for an RC circuit is the resistance times the capacitor, and the units for that turn out to be seconds. Okay, and so we have 10 kilo ohms times 15 micro. So remember that's micro is 10 to the minus 6. Okay, and K is 10 to the positive 3. And so that means that the time constant is 1 point, or no, sorry, 0.150 seconds. That's 3 significant digits. 0.150 seconds. That is our time constant. Now, what does that mean? It means that it's a physical representation of the circuit and how long it takes for it to charge. But it doesn't take one time constant. It takes a 4 to 5 time constants, depending on which textbook you read. Some of them say 4, but most of them consider 5 time constants to be a full charge. All right, so when we look at charging, so we have our time constant tau. All right, the first time constant means this will be time in seconds here, and so that would be 0.150 seconds. And the second time constant is going to be 0.3 seconds. And the third time constant would be, of course, 0.45 seconds. And the fourth time constant is 0.60 seconds. And the fifth one is 0.750 seconds. And just to kind of show you here, I'm going to also do the sixth, which would be 0.9 seconds. All right, so what we're going to do is we're going to calculate the voltage at each of those times. So initially, I forgot to save room for the for 0. I should have put 0 in here. So at time t equals 0, so at 0 seconds, we're assuming there's no charge on the capacitor. Okay, so at time t 0, 0, 0, right, there's no charge. Okay, and so the capacitor is uncharged, and so what that means is that there's no voltage on it, because remember that the voltage on a capacitor is equal to the charge divided by the capacitance. And since there is no charge, the voltage must be equal to 0. So if we know that the capacitor has been discharged, we know that there's no voltage on it, then looking at this circuit, when we come and look at this circuit, we know that there's 0 volts across the capacitor. And so we end up with a simple series circuit where we have our voltage source and a resistor, right? This is the first circuit we did in the class here. And so the current, we've calculated this current. The current I is simply the voltage, which is the 15 volts, the E Thevenin voltage, 15 volts divided by the total resistance, which is the 10 kilo ohm resistance. And so our current, when we first, as soon as we close the switch, okay, so a lot of times I like to kind of mark this as like time plus. So this means the switch has just closed. I've just closed the switch. Then my current I is just simply Ohm's Law, becomes the 1.5 amperes. Okay, 1.50 amperes. Simply Ohm's law. Okay, I'm sorry, it would be milliamps because that was kilo ohms. Okay, so it's 1.50 milliamperes because this did have a kilo ohm down here, right? There's a K there. Okay, so it's 1.50 milliamps when you first turn that current on. All right, and so once you do that, now this thing starts charging. But we know that the voltage across the resistor, when we first turned that on, the voltage across the resistor was the 15 volts, and the voltage across the capacitor was 0 volts. Okay. And the this last column my left here is just to calculate like the percent charge. The percent charge, how charged was it? Okay, and so it's not charged at all. Okay, there's no charge at this time. Okay, so it'd be 0.003 significant digits. So now when we want to calculate the voltage, okay, we calculate the voltage is equal to, this is the equation they gave us, it's equal to your voltage source times, which is E Thevenin in our case. Okay. So for our case, the voltage source would be E Thevenin here, and that would be times 1 minus the exponential minus t in time divided by RC. Okay. So for the first time constant, that the time is 0.15. So that is 15 volts times 1 minus e to the minus 0.150 seconds divided by 0.150 seconds. The seconds cancel. Alright, and if you calculate this, so this would be at your first time constant now, so I'm doing the first time constant, and my voltage across the capacitor at that time will be 9.48 volts. Okay, so what that means is if you calculate the percentage of that, that means that we have charged up to 63.2% of our total charge that we're going to put on this. So we've in that very first time constant, we've charged over 63%. All right, now we can use Kirchhoff's voltage law to calculate the voltage across the resistor. So the voltage across the resistor is simply E Thevenin minus VC. Right? And so now that's across this entire 10 ohm resistor here. Okay, so if you were looking for the voltage just across the 4K, you would of course have to do the voltage divider between the 6 and 4. Okay, so this, when I say VR here, it's the VR total. Maybe I'll mark that over here. This is total. Okay, the total VR. But that is simply, again, E Thevenin, which isn't changing, minus VC, which is changing as we put the charge on the capacitor. This is charging up, and so that leaves us about 5.52 volts across the resistor. Now we can calculate Ohm's law, calculate the current using Ohm's law. Remember, the current in the circuit is equal to Ohm's law, which says that it's the voltage across the resistor divided by the resistance. Notice Ohm's law doesn't say anything about capacitors. Okay? Ohm's law only applies to resistance, but we can calculate the current. We know it's a series circuit. We're looking at this modified circuit down here. It's a series circuit, so it's the same current everywhere. So the current through the resistor is the current going into the capacitor. And so that current then becomes 552 milliamperes. Okay, so the current has dropped by 63%. The voltage across the resistor has dropped by 63%, and the voltage across the capacitor has increased by 63%, and that's all within that first time constant. Okay, so within that first time constant, we've went from zero charge up to 63% of the full charge in a single time constant. Now, in the second time constant, we do the same thing. Notice up here, this was e to the minus 1.50, or I'm sorry, 0.150. This was e to the minus 0.150 divided by 0.150. Now, something divided by itself is simply equal to 1. Okay, so the first time constant, the e term, is e to the minus 1. Okay, so it's 1 minus e to the minus 1. That's where the time constant piece comes in. Okay, because we get a nice integer value up here in our e. That's what the time constant is basically all about. All right, so but now we're at the second time constant, so it's going to be 30 divided by 0.15, so it's going to be 0.300 divided by 0.150, okay, which is simply e to the minus 2. So we get this 15 volts times 1 minus e to the minus 2 at the second time constant. And that gives us the voltage across our capacitor here. And that turns out to be 12.9699 volts. Okay. And so if we round that up to 3 significant digits, then we would actually end up rounding that up to like 13 volts. Now that there is 86.4, or actually more like about 86.5% of full charge. So calculating our voltage using Kirchhoff's voltage law, we can determine VR is the 13 volts minus the 15 volts, which basically leaves us at about 2 volts. All right, and then our current is going to be then at about 0.2 milliamperes. Okay. Now, if we do the same thing, but now we got 45, so up here, we're going to have the third one, so we're going to have 0.450 divided by 0.150. There's a 1 in there somewhere. All right. which of course gives us a nice integer value of -3 in this equation. And so that's going to give our voltage across the capacitor is going to be 14.25 volts. All right, so we would basically say about 14.3 volts. And that gives us about 95.0% of full charge. So we're at 95% of our full charge. So that leaves us our voltage of about 0.7 volts over here on our VR, and so that gives us about 70 milliamps. Okay, or I'm going to leave it written like that right now just so we can see it dropping. Okay, but we would really want to say 70 microamps, right, to put that in Blackboard. And then the fourth one. Okay, so if we go to our fourth one then, and so this ends up being 0.60 divided by 0.15, which gives us that nice integer value of a -4 up there. And so we calculate VC using this equation again, and that gives us 14.725. So it's just call it about 14.7 volts. And so that's at like about 98.2% of full charge. Okay. And then our voltage is going to be about 0.3 volts. Which gives us, we're dividing that by 10K to get the current, of course. And then the, if we look at this, this was at 98%. And some books call that full charge. But most books go all the way up to the fifth one. So at the fifth one, this is going to be up here 1 minus e to the -5 up here. Right, because it's 0.750 divided by 0.150, and that gives us again that nice integer value. So we get 1 minus e to the -5, and when we do that, our voltage now becomes 14.898. Okay, so 14.898 volts. So we'll just call it about 14.9 volts to 3 digits, and that is 99.3% of full charge. Okay, so that's 99.3% of full charge there. And so when we do that, then our voltage over here now, right, that leaves us about 0.1 volt across VR, and so our current is about 10 milliamperes. And if we do a sixth one, then we would change this to a 6 up here. That gives us our voltage to be about 14.96. Okay, so 14.96 here. And if we rounded that then up to 3 decimal places, we would actually end up with our 15 volts. Okay, but I'm just kind of wanted to write this down here. It's, you know, we're not actually at 15 volts. We're only at about 99.75% of the 15 volts. And our voltage here then, if we look at the true actual voltage out to about 5 digits, that would leave VR to be about 0.0372 volts. All right, so it's close to zero, but it's not quite zero. All right, and then of course our current would be 372 milliamperes or microamperes, but it's, you know, it's actually microamperes if we move our decimal place. All right, so that is the charging of the capacitor. Okay, again, this time constants come from the fact that you end up getting a integer in this equation up here in your E term. So your E term, you get integer values. That's this magic of the time constant. Okay, but it takes about five time constants to reach over 99% of full charge. Now, I didn't actually take this out, but if you go out to 10 time constants, or even if you go out to say 30 time constants, you won't quite reach full 15 volts if you take it out enough decimal points. All right, because theoretically you'll never quite reach that 15 volts that we would be charging it up to. All right, so we like to just say that we have reached full charge at 5 time constants, and call it, you got to cut it off somewhere, so that's where we like